Hi everyone, I'm Anastasia Sofronova. My talk is about depth lower bounds for De Morgan formulas, and this is a joint work with Ivan Mikhailov. Let me start with the base question that concerns people in Boolean formula complexity, and that is, what is the smallest size and or depth of the formula computing a certain function? Now, a simple counting argument gives us that almost all Boolean functions are exponentially hard. But the funny thing is that we do not know any explicit example of the hard function. And in fact, proving any Boolean formula lower bounds is a notoriously difficult problem. Prior line of work includes papers by Subatovskaya, Hrabchenko, Andreev, other papers up to the celebrated result by Hosted, size n cube and depth 3log n lower bound. Later in this result, lower order terms were improved by Tal. But essentially, this has been the state of art for more than 20 years now. And it's not quite clear where do we go from that. The hard example for which Hosted's lower bound is achieved is called Andreas function. It is defined as on the slide. Andreas function takes n log n plus n bits and outputs 1 bit. First n log n bits are essentially an input. It's log n strings of n bits. And the last n bits are a description of a Boolean function f, which takes log n bits and outputs 1 bit. So we take those log n strings, and for each string, we zor n bits that are included in the string, and we feed it as an input to a function f. The lower bound for Andreev's function is proved by applying a random restriction to a formula computing it and estimating how this formula would shrink after this random restriction. And apart from that, there are not many working methods for proving any lower bound for Boolean functions. So the main problem here is what should be our approach to strengthening Boolean formula lower bounds? Well, Kaczmarz and Wigderson suggested the following approach based on block composition of two Boolean functions. So we have a function f, which takes n bits and outputs 1, and function g, which takes m bits and outputs 1. And we feed n instances of function g to a function f. Kaczmarz-Wigderson conjecture states that for any non-constant functions f and g, the depth of the formula computing their block composition would be roughly equal to depth of the formula for f plus depth of the formula for g. Now, upper bound for depth formula for block composition in terms of depth of formula for f and g is easy. It's easy to compute block composition in that much depth. The hard part is to achieve a lower bound on the depth of the block composition. Now, this symbol roughly equal can be treated in a number of ways, really. We can treat it in the strongest possible sense, like just equal and maybe minus some constant on the right side. And in fact, there are no known counterexamples for the strongest version of Kaczmarz-Wigderson conjecture. If this conjecture was proven, then P is not contained in NC1 would follow immediately. Let me give you the idea of the proof. It is quite simple. Let us just take a hard function f on log n bits, and let us compose it with itself log n over log n number of times. And the resulting depth of this composition would be too large for NC1, yet still it would be computable in class P. Here we use that every time we compose f with itself, the depth of the formula grows sufficiently. And in fact, we don't need even the strongest version of the conjecture for this proof to work. We would do just fine with the weaker versions. Now, suppose that for any function f, there exists a function g, such that if we define a composition of this function in any reasonable way, then after composing f with g, depth of the Boolean formula would be much larger than just depth for f and depth for g. For example, the following lower bound would suffice, that depth of the composition of f and g is bigger than just depth of the formula for f in like 1 plus epsilon times. And what's nice is that there are no known barriers that would prevent this technique from working, meaning that there is no reason that this conjecture should be wrong, apart from the fact that no one has proven it yet. In fact, we can take a look at the size version of this conjecture. Let's say that there exists function f and there exists function g, such that the size of their composition, again defined in any reasonable way, is large enough. Now here we have existential quantifiers for both f and g, which means that we cannot iterate this statement really, but still some better formula lower bounds would follow from that as well. Let us take functions on log n bits and just plug their composition into Andreas function. And then let us just repeat shrinkage argument by Hosted, and that would get better than n cubed lower bound. And in fact, there is another angle at which we can look at Karčmaras-Wigderson conjecture, and it is communication complexity perspective. Here we have two players, Alice and Bob. Each of them has infinite computational powers. But the input for the problem is split into two parts. Here Alice has X and Bob has Y, and they need to find some O such that XYO is in some relation R. Now, to solve this problem, they can send bits to each other, and the complexity measure of this problem is the number of bits exchanged in worst case. Let us now consider a Karčmar-Wigderson game. Here we have some function f, which is known to both of the players, and Alice has x, such that f of x is 0, and Bob has y, such that f of y is 1. And they need to find a bit of difference between x and y. Now, it just so happens that a depth of the Boolean formula computing function f is equal to communication complexity of Karčmar-Wigderson game for this function f. And in these terms, our desire to prove a lower bound for composition of some functions f and g can be translated to communication complexity terms as lower bound for composition of two Karčmar-Wigderson games, Karčmar-Wigderson game for f and Karčmar-Wigderson game for g. Let's keep that in mind and consider another relation, which is called universal relation. Here, Alice has x, Bob has y, and they need to find a bit of difference between those two strings or to determine that x is equal to y. Now, here we don't have any promise that is related to some function f, and lower bounds for this relation are not connected to any formula depth lower bounds. But researching lower bounds concerning universal relation can be seen as a stepping stone for our ultimate goal. And there is quite a number of non-lower bounds involving universal relation. For example, for the composition of two universal relations, for a composition of Karčmar-Wigderson game with universal relation, and the other way around. And you can see that the last results are actually quite recent. So it kind of seems that what we need is just one more push to achieve lower bound for composition of Kachner-Wigderson game with Kachner-Wigderson game, and to get rid of this universal relation completely, which is what we kept in mind. And in fact, the first drafts of our result were written in communication complexity language. What we wanted to do is to prove some kind of result which would be as close to some weaker versions of KRW conjecture as possible, but so that it could be also nicely translated into Boolean formula language. And in the end, we ended up getting rid of communication complexity language completely. And this is how I will present our result here. Let us consider now the composition introduced by Mikhailin and Smal. Here we have two functions f and g, and the function f takes n bits and outputs 1, and function g takes n bits and outputs also n bits. Our main technical lemma is formulated as here on the slide. With high probability for a random function f and any alpha less than 1/5, there exists a function g such that the composition of f and g is not computable by small n of small enough formulas. And here epsilon is an arbitrarily small constant. Now this is a depth lower bound of the form which is required in weaker versions of Kachner-Wigderson conjecture, namely depth lower bound 1 plus alpha minus epsilon n with 2 alpha minus epsilon and gates on top, unfortunately. So here we trade one layer in the lower bound for 2 layers of AND gates on the top of the formula. Let us just take this main lemma and plug it into Andreas function. So we call it modified Andreas function, and it takes now 3log n plus 1 n bits and outputs 1 bit. First, 2 n log n bits are 2 log n strings of size n, and this is input to our zero composition. Next, n log n bits represent a description of a function g, which takes log n bits and outputs log n bits. And last n bits represent a function f. And the scheme is essentially the same as with original Andreas function, though the shrinkage argument that we apply here is slightly different from one in Hosted's paper. So the theorem that we get is that modified Andreas function is not computable by an AND of n to the 2 alpha minus epsilon formulas of size at most n to the 3 minus alpha minus epsilon for any alpha less than 1/5 and epsilon is arbitrarily small constant. Let us now take a look at the idea of the proof of our main lemma. Suppose we have some set of functions g such that the composition of f and this function g do not agree on a lot of inputs for different g's. It looks just like here on this picture. And from that, it follows that union of one inputs of a small subset of this set G covers almost all inputs. Now let us consider formulas for these Zor compositions, and we will walk down the trees as long as we are in this top subtree of AND gates. Now, walking down AND gates reserves ones, meaning that if we have some AND gate that outputs 1 on some input, then all its children must output 1 on this input as well. Now we stop in some subformula after walking those AND gates, And now I want to say that for a lot of different functions G in this set G, we ended up in different subformulas. Now, suppose we have some large subset of this set G, for which the subformula we ended up in is the same. I want to say that this subformula must output 1 on all 1 inputs of all those functions. And that means that this subformula, in fact, outputs 1 on almost all inputs, because union of 1 input of this large subset of functions covers almost all inputs. Which means that this subformula we ended up with is almost trivial. And if we walk down AND gates in a smart way, we can ensure that we never end up in a trivial subformula. So this is our contradiction, and this is how we ensure that indeed for a lot of different G's, we ended up in different subformulas. And next we just apply a counting argument and say that for some G, the corresponding subformula must be big. So in order for this plan to work, we need to find a big enough set G with the needed properties. Let me explain how to find that set G. And in short, we use probabilistic method. To elaborate on that a bit more, here's the key lemma in finding G, which is due to Kaaver-Hosseini. And the main idea of this lemma is the following. The input for Zor composition is split into 2 parts, X and Y. So let us fix some X. And let us consider G of X for different functions G. So let us take a look at vectors that different G output on this fixed X. I want to say that if those vectors, those outputs are linearly independent, then those Zor compositions behave almost like random functions, which means that if we take K such Zor compositions, then the intersection of the zeros would have size roughly 2 to the n minus k. So that's kind of a very natural behavior for a random function, really. Meaning that if we add one more function G with one more linearly independent output on X, then the size of this intersection of zeros drops down like 2 times. Now, when we have this lemma, we do the following. Let us fix some X, and then we say that the set of outputs for different G's has high dimension with high probability. And if this set has high dimension, then we can apply this lemma, and most of the Y's that can go with this X produce 1 inputs. Now, we have some zeros naturally, even after applying this lemma. We have some Y's that in pair with this X produce zeros. And we also have some X's that have low dimension anyway, but that's fine. We can allow errors on those inputs, and the proof from the previous slide will still work. That is more or less everything that I wanted to say about the proof. And which open questions follow from this whole? The main one is obviously how to make this work in a general setup, meaning how to get rid of the requirement of AND gates on the top. And to start with, one could consider formula with few alternations instead of AND on top. And for example, one could start with CNFs or DNFs. That is all for my talk, and thank you all for listening.